Hello and welcome to this video on how to interpret confirmatory factor analysis results. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate methods including factor analysis, structural equation modeling, path analysis, multi-level modeling and latent class analysis. If this is something that interests you, then please consider subscribing to this channel. Also, don't forget to check out the description for additional resources, including workshops that I teach for QuantFish. In this video, I want to walk you through CFA, and specifically I want to discuss how to interpret the results of a CFA, and first of all talk about what are the relevant outputs that you get, the relevant pieces of information that you would look at when you run a CFA, for example in Mplus or Lavaan or JASP or Amos or some other software that can handle those types of models. So first of all, let's look briefly into what is confirmatory factor analysis. Here you can see an example of a two-factor model with two indicators per factor and correlated factors. So for example, I might be interested in looking at a model for two different abilities. One factor could represent spatial abilities and the second factor could represent math performance, and perhaps I'm interested in figuring out whether the scales or tests that I use for measuring spatial abilities and the tests that I am using for math ability properly indicate factors of spatial ability and math ability. And then also I might be interested in learning about how those abilities are correlated at the latent level. So a key question with CFA is about whether the factor structure that one hypothesizes is confirmed by the data or is found in the data, whether the variables measure the factors that they are supposed to measure appropriately, meaning with sufficiently strong loadings to where we can think, or we would assume, that the variables are reliable and valid indicators of their intended factors. And then also another goal is to determine discriminant validity between factors, to find out whether, for example, a spatial factor and a math factor show sufficient discriminant validity in the sense that they're not too highly correlated. Or in other cases, we might be interested in convergent validity between factors. For example, when the factors represent different raters of the same ability or construct, then those factors from different raters in the same construct, they should be highly correlated for convergent validity. So it really depends on our hypothesis what we expect for the factor correlations. But so that's to say very briefly what a CFA is about: testing a hypothesized factor structure, determining variable validities and reliabilities, determining construct validity, discriminant, convergent validity, and other issues related to the relationship between factors and variables. So what is the output that we are getting for a CFA? First of all, there's information about model fit. So that's the very first thing that we would always look at when we run a CFA, is indices of model fit to determine whether our model fits the data appropriately. And we want to do that before we interpret any of the parameter estimates, meaning any of the factor loadings or factor correlations or other parameters that we will talk about shortly. Second, once we determine that a model fits appropriately and we feel comfortable with the model, we can interpret the parameter estimates as well as their standard errors and tests of statistical significance if applicable. And then finally, we also are interested in Rsquared for our observed variables to determine the reliability of the measure. So we want to know how much of the variance in our observed measures is explained by the factors, and that's interpreted as an index of the variable reliability. When we have a more complicated factor model, such as a second order factor model where the factors themselves are explained by other factors, for example a second order factor, then we might also be interested in Rsquared for the first order factors if they are indicators of a second order factor, but that's not something that I will discuss here. But so say, just so you know, R² could also apply to the factors if they are measures of a second order factor. So let's take a look at these different outputs in detail. And so let's talk about model fit first, and I'll give you two examples here, one where the model fit is good and a second one where the model fit is really bad, so you can see how you would interpret that. And I'm going to use output from the Mplus software. You would find very similar output in other programs such as Lavaan, AMAS, JASP, and so on. So these types of indices are very common and they're found in different software programs. And so here's what it looks like in Mplus. You can see that the first thing that Mplus results is a chi-square test of model fit, and that's, so say, the standard, the most important test to look at for a CFA and also structural equation model and path analytic model. This is a rigorous test of the null hypothesis that the model implied data structure is in line with the observed data structure, specifically the observed mean and covariance structure. And so this means that when this test is statistically significant, then that null hypothesis is rejected. So we're looking for a non-significant test for a well-fitting model, which, as you can see here, we have. So here you can see the p-value for that chi-square test of model fit is 0.4726, which is greater than a common alpha error level of 0.05 that we typically use for tests of statistical significance. So here the null hypothesis does not have to be rejected and we can retain the model. We don't have to reject the model because the chi-square test of model fit does not indicate a significant discrepancy between our model and our observed data. Furthermore, we have closeness of fit indices or descriptive fit measures, as we say. The RMSEA is one of them, the root mean square error of approximation. And so under estimate, you find the point estimate. You can see it is 0 here, which is a good sign. That happens whenever the chi-square value for the overall test of model fit is smaller than its degrees of freedom. So here the chi-square is only 0.516 and the degrees of freedom are 1, so therefore the chi-square value is smaller than df, and as a result RMSEA will be 0. Now, what should you look for in RMSEA generally? We tend to think that RMSEA values that are smaller than 0.05 point to a well-fitting model generally. This doesn't apply to all scenarios, but as a rough rule, we would look for RMSEA values smaller than 0.05. Furthermore, we have so-called comparative fit indices that compare the fit of our model to the fit of a baseline model that assumes that the variables are not correlated, that the covariances between all observed variables are 0. And that model typically fits very poorly. And so we're comparing, so say, incrementally what our model or how much our model fits better than an independence model. Therefore, these indices are also referred to as incremental fit indices, and there are many of them. Mplus reports the CFI, the comparative fit index, and the TLI, the Tucker-Lewis index, and those should be close to 1 for a well-fitting model. In this case, you can see they are exactly 1, which is great. So that also points to a well-fitting model. Generally, those indices should be above 0.95 for decent model fit. They can even be above 1, so that happens sometimes. It's not a sign of a problem with the model. It just typically means your model fits a lot better than the baseline model. And then also another index that is frequently looked at is the standardized root mean square residual, which is a summary measure of the residuals. The residuals here are the elements of a covariance matrix that looks at the difference between the observed and the model implied covariances and variances, and so it summarizes, so to say, the discrepancy between model and data in a single index. And that index also, like the RMSEA, should be smaller than 0.05 for a well-fitting model. Here you can see it is very close to 0.003, which means that there are hardly any residuals here that are meaningful. So this model reproduces the observed variances and covariances very well. This is a very good model that we would most likely not change in any way, because the fit is so good that unless we have other concerns about this model, we would go with that. This looks really, really good. Now let's take a look at an example where the model fit is terrible, so you can see a little bit of a contrast. And so here is really poor model fit. You can see the chi-square here is 71.897, 3 degrees of freedom. So the value is much larger than the degrees of freedom. Actually, this is really terrible. So this is so much larger than more than 20 times as large as the degrees of freedom. The p-value is extremely small, meaning the model is rejected. So the null hypothesis can be rejected that the model fits in the population. So that's totally showing already that this model is not what we want. The RMSEA is 0.25, which is also really bad. CFI, TLI are below 0.95. Remember, we would like to see them to be 0.95 or greater. And the SRMR is also huge with a value of 0.127, indicating that there is a large average residual in our residual covariance matrix, which is indicating that the model does not reproduce the observed variances and covariances very well. This model does a poor job. It's underfitting the data. There's not enough in the model, so say, to reproduce our observed variances, covariances, and potentially the means also. So this model would be absolutely rejected, and there would be no way we would use this model. We would not even look at the parameter estimates probably, and definitely if we do, we should interpret them only with great caution, because they are likely biased due to the model fit being so poor. Now, the next thing that you would look at if you have a model that looks like our first one that has a good model fit is the parameter estimate. So you would take a look at the model results, and specifically you would take a look at factor loadings, factor variances, factor covariances, and the corresponding correlations, residual or error variances for the indicators, potentially residual or error covariances and correlations if you allow those, which is not the case in standard CFA, but in some CFA models you might have correlated errors as well. And then intercepts may be looked at for the indicator, so additive constants in your measurement model, and potentially latent means in specific CFA models. So let's take a look at some of these based on the Mplus output, and we're going to start with the factor loadings. And so in Mplus and other programs, typically you get the unstandardized parameter estimates, the unstandardized loadings and other parameters first, meaning this is a solution where neither the observed nor the latent variables are standardized. So unlike an exploratory factor analysis where everything is standardized and you get standardized loadings, in CFA that's not typically the case, and that's a source of frequent confusion among novices who know EFA but who are only about to learn CFA. They find those unstandardized factor loadings to be confusing. And so here's what it looks like. You can see that I have two factors. I have one factor that has indicators MRT1 and MRT2. So those are two measures of spatial ability, mental rotation. And then I have a second factor with two math scales as indicators of that factor. So my second factor is a math factor. And you can see that the first factor loading is exactly 1.0. That is the point estimate. And that's actually not an estimate, because this factor loading is fixed. And that has to do with identification constraints in a CFA. In CFA, we need to put certain constraints in the model to have an identified model that can be estimated. And one default constraint in many CFA programs is that one factor loading per factor is fixed to 1 for identification. And then that factor loading does not get a standard error, SE, or test statistic or p-values. You can see Mplus put a 0 here for the standard error and put a 999 for the estimate divided by the SE, which is a Z statistic. and also put a 999 for the p-value. So there's no significance test available for a loading that is fixed because it's not an estimate. And so this is normal for an unstandardized solution. We don't have to worry about it. It's kind of arbitrary which loading we fix. We could also estimate the loadings and instead fix the factor variances for identification. And it does not affect the key parameters that we are interested in our model, as we will see. The second factor loading then is freely estimated, and so it's estimated to 0.904, which shows us that the two variables have fairly similar loadings because 0.904 is pretty similar to 1. So these indicators are measured on about the same scale with the same units of measurement, or closely to the same units of measurement. There's also a standard error for this factor loading and a z-statistic, which indicates that the loading is statistically significantly different from 0 because the p-value here at the end is very, very small. And so that shows us that the null hypothesis that the loading is 0 in the population can be rejected. That's one very basic test to make sure that the variables really measure the intended factors. If you find that a factor loading is not significant, that would give you pause, and then you would have to think about what went wrong with either your model or this variable, because the variable should have a significant loading on this factor at a very minimum. Later we will see that that's not the only requirement for a good measure to have a statistically significant loading. It should also be substantial in terms of its standardized factor loading. But so that's a very minimal, so say, test. Now, often when a loading is not significant, it indicates that you have a problem with your model, and often it has to do with a large standard error, which might indicate that the model is under-identified, or that the model is over-parameterized, or that there's some other problem with the model. So you want to look at the standard errors, and you want to make sure the standard errors are reasonable in size relative to the parameter estimate. So they shouldn't be very large relative to the size of the estimate for a parameter where you assume that that parameter should be statistically significant. If you have high standard errors for loadings that should be significant and then they are not significant, that could be an indication of a problem with your model or data. You can see that for the second factor we find a similar result. The first loading is fixed for identification. The second loading is slightly different from 1. So these also seem to be measured on about the same scale with the same units of measurement. You can see the second loading also is statistically significant, which is as it should be. Now, more interesting than these unstandardized loadings are the standardized loadings, which have the same interpretation as an exploratory factor analysis when you have orthogonal factors or uncorrelated factors. So the standardized factor loadings, which you find under the standardized model results section in Mplus, are interpreted as correlations between each variable and its intended factor. So, for example, 0.828 is the correlation between MRT1 and F1. So that's a fairly strong correlation, meaning this is a good measure of that factor. And also the second loading, the second standardized loading, is also 0.829, very close. So both of these seem to be good measures of the mental rotations or spatial ability factor. The math scales have slightly smaller standardized loadings, so smaller correlations between variable and factor, so they're not as reliable. There's not as much true score variance in these math indicators as there is in the mental rotations indicators. In other words, the math scales appear to contain more measurement error. Now, one question that you might ask is, why are these standardized loadings different? Why is not one, or why is not one fixed to 1? So how is it possible that they're both estimated for each factor, whereas the unstandardized loadings, as we saw previously, we had one that was fixed to 1. And the reason is that in the standardized solution now the factor variances are fixed to 1, because by definition in a standardized solution observed and latent variables are standardized, meaning they have variances equal to 1 or standard deviations equal to 1. And so then both loadings can be estimated on each factor. So these are interesting and have a clear interpretation because they are correlations between the variable and the factor. Now that applies only as long as you have a simple structure where each variable loads only onto one factor and you have no cross loadings, because the factors here are correlated. So when you have correlated factors and you have cross loadings, then this interpretation does no longer apply, and then those would be partial standardized regression coefficients that you could not interpret as correlations. But here we have a perfect simple structure. Each variable loads only onto one factor, and therefore we can interpret those standardized loadings as correlations between each variable and the factor. Next, we have factor variances and covariances. And so the variances are given for F1 and F2. Now these don't have a super intuitive interpretation because, as we know, variances are squared standard deviations. So a standard deviation would be easier to interpret because it's in the units of the original variable. But here those are squared standard deviations, the variances, so they're not super clearly interpreted. Nonetheless, they may be valuable in some models. For example, when you want to conduct a variance decomposition or something like that. So those are parameters that you might want to report when you report the findings of a confirmatory factor analysis. There's also the covariance here that is given under F2 with F1 in Mplus. And again, the covariance does not have a clear interpretation or easy interpretation because it's not standardized, so it depends on the sizes of the variances of the variables. So it's difficult to say whether this covariance of 1.081 indicates a strong relationship between the math factor and the mental rotations factor, or whether that's a small relationship or what it is. The only thing we can see here is that the covariance is statistically significant and it's positive. So this means there must be a positive linear association between the spatial factor and the math factor, but we don't see easily here how strong that relationship is. However, we can see that again from the standardized solution where we find the correlation between factors. So when you standardize your factors to a variance of 1, then their covariance can be interpreted as a correlation. And so that's the case in the standardized solution in Mplus, the completely standardized solution. And so here you find under F2 with F1 a correlation of 0.338. So we can see now it's a medium-sized linear association between spatial abilities and math here in this data set, and the correlation is statistically significant. The p-value here is very, very small. So there's a significant positive medium-sized correlation between spatial ability and math at the latent level. Why is this factor correlation a valuable product of the confirmatory factor analysis? Because it gives us the correlation between true score variables. So it's basically a built-in correction for attenuation. If you have heard about classical test theory before, then you know that in classical test theory there's a correction for attenuation that allows us to estimate the correlation between true scores based on the observed correlation between variables and their reliabilities. And so here, this correction for measurement error that would attenuate the correlation between observed scores is built into the CFA model. As part of the estimation of the parameters, we get a latent correlation estimate that is corrected for measurement error, where this correction for attenuation has already been applied. And that's nice because it means that this correlation gives us a more accurate picture of the association between those constructs because it's not watered down by measurement error. So that's an important product of a confirmatory factor analysis, is that we get these latent correlations that are corrected for measurement error. Finally, we also get residual or error variance estimates as part of the model results, and those give us the residual variance component in each observed variable that is due to error, or at least is not due to the factor that is measured here. So that would either indicate random measurement error, or specific variance, or a combination, so something that's variable specific and not shared with the other indicators of the factor. Now again, these don't have a super intuitive interpretation, but in conjunction with the factor variances, we could see what proportion of the total variance is factor variance versus is error variance. Now, one other thing that we get in the output in many programs are intercepts. And so the intercepts are additive constants in the measurement model, and they in a standard cross-sectional CFA model do not have a super interesting value, so say to us, because they simply give the observed means. So they simply tell us what the means is as long as we don't include a latent mean structure. So those just simply reproduce the observed variable means, and that's often not so much of interest. Intercepts become more interesting when you have a multi-group analysis where you compare different groups, or when you have a longitudinal CFA model where you look at mean change across time, because in those cases the intercepts have to be tested for measurement equivalence or measurement invariance. So then we would check whether they are the same across groups for a given variable and or the same across time for a given variable. So they play an important role in multi-group CFA and in longitudinal CFA. For both of these, I have separate videos here on this channel that you can check out if you're interested in that as well. So intercepts we can typically ignore for a cross-sectional single group CFA, and also latent means are not estimated by default usually when you have a cross-sectional single group CFA, because they're not of interest, but latent means would be of interest in a multi-group CFA where we want to compare means across groups, or also in a longitudinal CFA where we would be interested in comparing means across time. Now, one last thing that we would typically look at in a CFA is R-squared. R-squared, here are the squared standardized factor loadings, and they have a specific interpretation in terms of the variable reliabilities in the sense of classical test theory. So the squared standardized factor loadings are equal to R-squared, and they're equal to reliability if you interpret the models in the sense of classical test theory. So this would then indicate that the reliabilities of these indicators range between 0.507 and 0.687. So between 50.7% of the observed variance and 68.7% of the variance. Here is true score variance, meaning reliable variance. And so the remaining portion would be error variance and or specific variance. So you can see that these indicators are not terribly reliable. So the reliabilities, the amount of true score variance here only varies between about half of the variance and 2/3 of the variance. And then between 50% and or between 33% about and 50% of the variance are error variance. That's not super good. However, remember that those are components of a test. So MRT1 and MRT2 are two test halves of a spatial abilities test, and so they would typically not be looked at or used in isolation, but rather combined into a sum score or composite. And the same for the math test. So math 1 and math 2 are two subscales of a math test that would be combined into an overall score. So what's more interesting than these individual reliabilities is composite reliability. So what would be the reliability of the sum for the spatial ability test and also of the sum for the math test? And you can also get that as part of a CFA. Now, Mplus does not currently output composite reliability, but other programs do. For example, the JASP program, which is free and for which you can find videos on this channel here where I show how you can run CFA and JASP. actually do have an option for composite reliability, which is very nice. And so I ran the same model also in JASP, and I got this nice composite reliability output here with coefficient omega. Coefficient omega is one composite reliability coefficient that applies when measures have different factor loadings, like in this case. And then coefficient alpha is Cronbach's alpha, which you may have seen in SPSS or in other contexts. And so Cronbach's alpha applies if the variables had the same loadings. Now we saw that in our case, the unstandardized loadings were both pretty close to 1, so they were very similar. So as a result, coefficient omega and coefficient alpha are very similar for a given factor. Here you can see for the MRT factor or composite score, the omega would be 0.814 and alpha is 0.812, very, very similar. So if you aggregated MRT1 and MRT2 into an overall sum score or composite, then that composite has a reliability of 0.81, which means 81% of the variance in that composite is true score variance, and that's much, much better than the reliabilities of the individual scales. And the math test overall would have a composite reliability of about 0.72, so about 72% of the variance in the composite, the sum of math 1 and math 2, would be true score variance, which is also a lot more decent than those individual reliabilities of the individual subscales. I hope you found this video useful to learn about how to interpret the results of a confirmatory factor analysis. If you did, then please consider subscribing to this channel, and don't forget to check out the description for additional resources, including workshops that I teach for QuantFish, and I'll see you next time.